Our ability to detect and probe matter at its most basic level has provided us with ever greater insight into how the universe works, how it was formed, and where it's going. However, it has also revealed the limits of our understanding, with only 5% of the universe known to us. To explore the remaining 95%, the international community has come together to build the International Linear Collider, a high-energy electron-positron linear collider with superconducting accelerator technology.
One thing we look at understand at ILC is the nature of this newly discovered particle called the Higgs boson. Every particle we have seen before is spinning, but Higgs boson isn't. And the way we are trying to make sense out of it is maybe that it's spinning in extra-dimensional space. Maybe the composite particle has a spin structure inside. But if none of these things actually turn out to be true, maybe it points us to the new direction of talking about multiverse. So we are at the juncture of trying to decide which way we're supposed to go, and ILC would really help us decipher what exactly the Higgs boson is and where we should be going next.
The ILC was initiated in 2005 and immediately gained the support of high-energy physics communities across the US, Europe, and Asia. These initial efforts culminated in the Technical Design Report in 2013.
I've had the privilege to work on some of the biggest scientific projects, building particle accelerators over more than 40 years. The next big step will be the realization of the International Linear Collider. The technology is now very mature. We have no difficulties there. It can be done, but it needs one nation to lead and to open up the negotiation procedure with other countries. There is a very strong interest in hosting the ILC in Japan. It is good for science, it's good for international collaboration, and it's good for Japan.
The ILC will consist of 2 linear accelerators throwing 10 billion electrons and their antiparticles and positrons toward each other at near light speed. Across a 31-kilometer distance, the beams will collide 14,000 times a second at extremely high energies, with every collision creating a new array of particles for scientists to observe. The technology and expertise needed to realize the ILC is being developed all over the world. In Germany, the construction of the European XFEL, an electron laser facility, demonstrated that the industrial-scale fabrication of required superconducting cavities and accelerator modules was possible. At Fermi National Accelerator Laboratory in the United States, scientists are focused on developing a new production process allowing for far more efficient superconducting cavities. Detectors are also an essential part of the ILC, with a wide range of capabilities being worked on.
The global worldwide community has been working on detectors for a decade, and those include vertex detection, tracking, and calorimetry. One particularly strong advantage of the detectors is the high level of granularity, which will enable precise measurements of the Higgs boson, the top quark, and other new physics searches.
In Japan, preparation for the construction of ILC is well underway. At the High Energy Accelerator Research Organization, or KEK, in Tsukuba, a wide range of research goals are coming together.
At KEK, we have been working on the development of accelerator technologies, detector technologies, and also on preparation of physics analysis, which is important to maximize the scientific outcome from the ILC. KEK is strongly committed to play a leading role in getting green light for ILC.
This is the Accelerator Test Facility, ATF. ATF is a facility to develop the high-quality small-size beam, so-called nanobeam. ATF is operated with international collaboration, and various components are coming from institutes all over the world. This is ATF-2. ATF-2 is a prototype of the final focus region of the ILC. The goal of the ATF-2 is around 37 nanometer in beam size, and we have already achieved 41 nanometer. This is a world record. This is a damping ring. We can improve the beam quality by circulating the beam inside the damping ring. This is Superconducting RF Test Facility, STF. The aim of the STF is to develop the superconducting RF system required for IFC. Total system development is essential for the real project. We use the superconducting cavity like this in order to accelerate the beam. We adopt highly pure niobium as a superconducting material. Total 18,000 cavities will be used in the ILC.
With Japan as the likely host of the ILC, the Japanese government is seriously looking at the issues around hosting the project.
安倍総理の国会の所信表明演説につきましても、従来の宇宙開業に加え、加速器がイノベーションの源泉として登場し、そしてここ数年の間は特に実現に向けた国際的な環境を作るために我々も力を注いでまいりました。
Japan's world-leading industrial sector is also playing a key role, with the Advanced Accelerator Association leading the way for industry collaboration.
AAA was established in 2008. This was organized as a joint effort between industry and academia to promote the science and technologies of advanced accelerators, in particular aiming at the ILC host.
With the realization of the ILC in sight, Japan is ready to host scientists from all over the world.
The ILC will be the first worldwide international laboratory for frontier science in Japan. The Japanese public is eager to live and work together with world scientists and their families. I am working hard to welcome the ILC here in Japan.